Thank you very much. Thank you for having me. And I understand that it's still kind of like early New Year, so I may not get the crowds that you guys might usually get. But let me talk about this project. And this is basically like a short preview of where we are right now. The project, the Regional Arctic System Model, has been funded primarily by Department of Energy and Office of Naval Research. Department of Energy for longer term modeling and simulation, Office of Naval Research for short time hindcast and prediction. In addition, we also have support from National Science Foundation on the marine biogeochemistry development and science. And we've been heavily using the computer resources from the DoD High Performance Computing Modernization Program. I want to acknowledge all my co-authors. Most of them are the RASM team and collaborators from Los Alamos, which are part of this HILAD RASM project that we're currently in phase 3, funded by Department of Energy. So just brief outline, I'll provide a one-slide overview of the RASM configuration for those people who may not be familiar with the Earth system models. I'll provide some examples of RASM evaluation, including simulation of observed extreme events in space and time. And I'll discuss some results on RASM dynamical downscaling, including the NCEP CFS intra-annual forecast, probabilistic forecast, and downscaling, decadal time downscaling using CSM, decadal predictability large ensemble, and latest one with the E3SM downscaling, and I'll summarize with some comments at the end. So RASM configuration is, okay, so the schematic diagram on the lower right is basically your typical Earth system model, which includes the atmospheric component, in our case, WRF, ocean model, a sea ice model component, land hydrology, stream routing model. And we also, as I said, under NSF sponsorship, we have developed or included marine biogeochemistry into the ocean and sea ice components. Everything is coupled using the flux couplers, energy and mass conserving. And this is a regional model, so we need to have a lot of boundary conditions from a global sources, either the reanalysis, global atmospheric reanalysis, or Earth system models if we're talking about some projections. The important part of the configuration is that we're not using any data simulation results that we present, and including the forecast. There is no bias correction. The hindcasts that are simulated with the just the high fidelity physics allow us to provide physically consistent initial conditions across ocean and sea ice model components, which are important. I'll discuss this later. And most importantly, the results from hindcasts can be compared against observations, which is not necessarily the same case when you're running the Earth system model and you have the historical simulation that not necessarily can be compared against observations. So the first results I wanted to discuss is the heat convergence of the Barents-Kara Sea compared to the Central Arctic heat convergence in the configuration of the RASM model component at 9-kilometer force with atmospheric reanalysis, Japanese reanalysis 55-year. And what I wanted to point out is that the net heat flux convergence of the Barents Sea is close to 70 terawatts, and whatever remaining flux convergence of Atlantic and Pacific water entering the Central Arctic remains only about 10 terawatts. So if you compare those two magnitudes in a pan-Arctic sense, more than 80% of the total heat convergence into the pan-Arctic is actually lost or used up over the Barents-Kara Sea. And that's a very important aspect, because if you go to a coarser resolution, we can configure global reanalysis forced RASM configuration at 1 degree. And you can see that only 30% of the oceanic heat convergence is used up or lost over the Barents-Kara Sea, and much more is actually delivered into the Central Arctic compared to the previous 9-kilometer results, 10 terawatts. Here we deliver close to 40 terawatts, which is 44 times more. And that has significance both for the Barents Sea as well as the Arctic Ocean. Now, the reason for the difference in the simulation of the oceanic heat convergence can be exemplified by the section, hydrographic section between Norway on the right panels here and Spitsbergen on the left. So left is north, right is south. This is the temperature profile across that section from the 9-kilometer model. And I'm pointing out with the arrow here that in that resolution, we're representing the very warm and fresh coastal current called the Norwegian coastal current. If you look over the 1-degree sections, that feature is not available in those simulations. And the big deal is that the Norwegian coastal current in the 9-kilometer simulation accounts for about half of the heat and volume fluxes into the Barents Sea. So some of the problems with the coarse resolution simulation is that if you don't account for the Norwegian coastal current, your Norwegian Barents Sea heat convergence will be misrepresented, and so consequently the heat converges into the central Arctic. So the main thing is that if you look at the 9-kilometer model simulations, this is a monthly mean from a year in the past, from 1994 March. The shading here represents the turbulent heat fluxes, latent and sensible heat fluxes in a monthly mean sense. And the scale is shown here to be in watts per square meter. So if you look at those blue type spots here along the marginal ice zone in the Norwegian, Norwegian Greenland and the Barents Sea, you can see that large fluxes, order of 200 to 300 watts per square meter in a monthly sense, are removed from the surface ocean via turbulent surface heat fluxes into the atmosphere. And those fluxes might be controlled by mesoscale ocean dynamics. So those were results from the regional Arctic system model. We have looked at the E3SM simulations where we have refined Arctic configuration down to 10 kilometers, so comparable to the 9-kilometer RASM. And we have comparable volume and heat fluxes into the Barents Sea from that simulation, 2.75 Sverdrup of volume, 77 terawatts of heat input. When you look at the low resolution E3SM, which is 30-kilometer resolution in the Pan-Arctic region, the heat and volume fluxes are significantly lower in the global ocean simulations forced with the reanalysis as well. So this is not just an artifact of original model. This is also a bold representation due to the difference in resolution in the global ocean simulations as well. Now, the importance of this is that if you look at the changes in the heat convergence into the central Arctic, I don't have time to go to show the previous results, but in RASM simulations, if you deliver order of 40 terawatts into the central Arctic in terms of the oceanic heat convergence, we basically melt out the sea ice in the summertime by early 2000. And the way that it's actually divided, you can see that on the upper left panel, the central Arctic receives more than 10% now, or 20%, roughly more like 30-40% of the total heat convergence. And the Barents and Kara Sea are releasing less heat over that region compared to that total that you can look up at those simulations here for different decades shown right here. And this is a regional Arctic system model. So again, the concern is that what does it mean if the global ocean models and the global Earth system models have the similar representations? So we found one of the results from the CSM high-res contribution to CMIP6 high-res contributions. And we found that the Arctic convergence in that simulation was 69 terawatts. And similarly, in that case, the ice was completely gone in late 1990s, early 2000 in CSM simulation. And you can see the division of the heat convergence of the Barents Sea and the heat convergence of the central Arctic from the CSM high-res contribution as well. So now we're switching gears and we're moving into what can RASM do in terms of representing extreme events in space and time as observed. I don't have time to talk about in details, but we have looked at the Typhoon Merbuk that was in 2000, 22 September made a lot of damage in the central Bering Sea along the western coast of Alaska. And we actually have that Mayor Book representation in terms of the sea level pressure, as well as the sea level height accumulation along the coast of Alaska at the same time when Mayor Book was actually at its maximum, sometime 16, 17 September 2022, according to observations. I'm not going to show the animation. Another big event was on the other side of the Arctic or Pan-Arctic in the Barents Sea. It was the late January 2022 extreme cyclone that was actually discussed in a paper by Blanchard, Wigglesworth et al. In 2022, one of the largest cyclones recorded ever in the region. And this is showing the sea level pressure map on the left from the RASM WRF model, and we're showing response in the sea ice drift being pushed to the north away from the central Barents Sea, releasing, opening more ocean surface to removing turbulent heat fluxes in response to that cyclone passage. Finally, we also looked at the mosaic drift that was extremely anomalous drift, accelerated drift according to observation. And now, if you look at the right panel, this is the anomaly in sea ice drift according to the satellite estimates anomaly from ALCI-SAF, European satellites estimates. And the right panel is showing the comparable sea ice drift anomaly from RASM for the period of January, March 2020, relative to the mean of 2010-2019. And its results are discussed in a paper in Cryosphere by Detlef, Masłowski, and all. So in terms of the probabilistic forecast, since 2019 January, every month we're producing order of 30 ensemble member forecasts initialized from the RASM hindcast forecast, which are shown in the middle here at the top. And we produce those forecasts as a sample mean that is shown in the bottom middle panel as the September 2017 forecast initialized on April 1, 2017. For comparison, the cryosat observations composite around the April 2017 are shown on the upper right, and with a different scale, composite of the cryosat estimates in late September, early October is shown in the lower right panel. And the CFSR initial conditions at the top and the forecast at the bottom is showing how unrealistic are the initial conditions in CFSR, both for initial and the forecast, compared to observations and compared to what RASM is performing. Keep in mind that RASM is using CFSR as the lateral boundary conditions to drive the regional model. So we are using CFSR, and our hindcast is delivering those initial conditions compared to the CFSR initial conditions in the hindcast on the left. And our forecasts seem to be highly influenced by the initial conditions 6 months earlier, and so forth also is represented in the CFSR. You can see the very thick and realistically thick ice in the buffer sea present in April 2017, which doesn't melt through September of 2017 as well. Now, we did the longer term downscaling using CSM large ensemble, and I'm showing just an example of the results. The CSM initial conditions January 2016 compared to the RASM hindcast produced initial conditions on the right for January 2017. The September 2016, CSM is having very thin, almost no ice within that first summer that we are using as a lateral boundary condition, while RASM is producing relatively realistic ice thickness distribution and ice cover. 10 years later, when we go to September 2025, CSM actually has increased the ice cover and thickness in summer, and RASM has been declining in the ice cover and thickness in over 10-year period. And again, keep in mind that RASM is using CSM large ensemble atmospheric boundary conditions for its 10-year downscaling hindcast. If you compare the RASM and CSM DPLE sea ice edge at the top and sea ice volume at the bottom, you can, against the NSIDC ice extent estimates in the top with the dashed black line, you can see that RASM doesn't have the biases that CSM has, especially in the winter time, maximum cover, exaggerated compared to the dashed line from NSIDC and RASM red line. In terms of volume, we don't have much of comparison, but we're using Pyomas as the reference, which is commonly used. And you can see that the blue line, which is CSM ice volume, starts low ice volume in the beginning of the 10-year period, and then gets very high volume above CSM and above RASM over a 10-year period, while RASM red line, it's relatively similar or level difference between biomass estimates of the total ice volume. So the message from here is that RASM physics dominate at the surface state and allows us that if there is a global model that we're using and has some biases, those biases from the global model are not carried into the downscale simulations using RASM. One more with the E3SM, similar simulation. I'm just showing the time series of the almost 40-year ice volume. The blue is the E3SM simulation. The red one is the RASM simulation. And the shading is just the estimate of the range of the observed biomass sea ice volume estimates. So you can see that red line has stabilized very quickly over a 35-year period. And the blue line has a very dramatic drift over 25 years. And then that drift is maintained through the remainder of the simulation. And again, if you compare the simulation at the top of the ice thickness distribution from E3SM, you can see unrealistic ice thickness in September exceeding 7 meters per of ice thickness in the central Arctic, compared to much more realistic ice thickness distribution in the lower panel from RASM. So again, very similar conclusions as with CSM. RASM physics dominate the surface state, and it doesn't carry E3SM Arctic biases over a 35-year period of the downscaling. Final slide is that we compare the CMIP6 ice extent, integrated ice extent error. So that's a new metric that we're proposed in this paper by Watts et al. 2021. And it's basically a spatial analysis of the errors in the total ice edge cover, and not comparing just the scalar of sea ice volume as just a number. So you can see that CMIP6 results are shown with all different lines, and they start somewhere between 1.5 and 2.5 million kilometers square as the winter minimum, and during the summertime they go up to 3 million square kilometer biases. RASM is very low, comparable to uncertainty in observations during the winter time, and has significant biases during the summertime related to the delayed in phase of ice melt and ice freeze up, which is causing those significant biases in the summertime. And again, is discussed more in this paper by Watts et al. 2021. Finally, comparison with the Pyomas. If you look at the cryosat comparison of the winter 2013, 2003, 2008 as a scatter plot, the left panel is the RASM scatter plot against cryosat, and the right panel on the bottom is the Pyoma scatter plot. You can see that RASM actually definitely is doing as well as Pyomas, maybe better, because it doesn't have the bias for the thicker ice in terms of the comparison with the cryosat. And that's also being discussed in this paper by Watts et al. In 2021. So in summary, RASM is semi-operational, fully coupled regional climate model, provides the benefits of high resolution, polar optimized physics and computational cost for synthesis of limited observations, allows resolving observed extreme events in space and time, and is readily available for further process level physics improvements. Dynamical downscaling using the fully coupled RASM offers robust gains in terms of more realistic simulations of Arctic climate, provides physically consistent initial conditions, which appear to be relevant for up to decadal prediction, And finally, demonstrate potential for improved subseasonal to decadal predictive skill of relevance to Arctic and other stakeholders. And we're currently doing a rigorous evaluation of model skill in the paper by Lee et al. In preparation. Thank you.
I see a question in the chat from Fred Bingham. What data are used for river runoff?
So for river runoff, when we're doing the reanalysis forcing in the Arctic, which would be ice ocean force simulations, we're using JRA 55 products. When we are running the fully coupled RASM, which most of the results I've shown here are fully coupled RASM simulation. As I said, we have our own RASM RVIC scheme, which is taking the, here we go, I'm sorry, which is taking the land hydrology from the VIC and delivers to the coupler to the stream routing scheme, RVIC, and then delivers to the ocean. So we're not using any data. We're actually actively predicting the runoff from land to the ocean.
Excellent, thank you. A quick follow-up. What are your plans with the cessation of JRA?
So we're already working, we're almost testing the ERA 5. The only concern is that both ERA 5 and all the other reanalysis, they've had this winter surface air temperature bias, significant bias, order of 5-10 degrees. And we hear from the community that people have new products with those biases corrected, but those biases are not available in the latest release reanalysis. So we're kind of like not rushing to the ERA 5B. We hope that maybe once we really switch from JRA 55, those biases will be corrected, because if we're focusing on the Arctic, those biases are significant, and they're related to misrepresentation of lack representation of snow cover wintertime in the Arctic reanalysis.
Wiesław, happy 2024.
Hi, John.
Question about, you started your talk talking about the differences in the 1 degree versus 10 kilometer stratification and such in the Barents Sea area. And if I heard you right, you said that at 1 degree resolution, your Norwegian coastal current heat flux up to the north was less, yet you have more heat flux into the deep Arctic.
Correct.
So how do you rationalize that? Is it that when you have a stronger representation of heat flux in the Norwegian current, you melt more ice and you lose the heat as a result?
So what happens is just, I have to go in details through those two slides here. If you look at this number on this slide, the heat flux convergence of the Barents Sea is 70 terawatts almost.
Yeah.
And the remaining flux into the central Arctic is about 10. So the total is about 80 into the pan-Arctic.
Yeah.
If you go to the 1 degree, we only lost about 16 terawatts in the Barents-Kara Sea, and we delivered close to 40 into the central Arctic. But the total is about, I had that number, 54, 55 terawatts compared to like 89 in the 112 degree, 9 kilometer RASM. So what happens is that in the lower resolution model, the Norwegian coastal current is not represented. There's a total less heat converges into the pan-Arctic region. And more importantly, out of this less, even less is lost over the Barents-Kara Sea and more delivered into the central Arctic. And that's why I had this comment in this slide that the mesoscale simulations over the central, mesoscale ocean dynamics is important in representing the turbulent heat fluxes over the Barents-Kara Sea to the atmosphere.
But why do you get more heat into the deep ocean at 1 degree resolution?
It's not that we get more, we lose less over the Barents-Kara Sea.
You showed me it was 40 versus 10.
Yeah, so what I'm saying, John, is that out of 89 in the 9 kilometer, we lose 80 over the Barents-Kara Sea, and only 10 is delivered to the central Arctic.
Right.
in the 1 degree, we have about 55 terawatts for the Pan-Arctic. We lose only 16 over the Barents-Kara Sea, and 30-something, 38 is delivered to the Central Arctic.
Is that because you have ice cover in the 1 degree simulation that inhibits the air-sea exchange over the Barents and Kara Seas?
Typically, it's not just the ice cover, it's just less mesoscale processes, misrepresentation of the mixing and the mesoscale processes affecting the surface turbulent heat fluxes over the Barents-Kara Sea.
Okay, thank you.
Thank you.
With 1 minute remaining, I will selfishly answer or ask a maybe too long question. But so I'm really interested in these results that you are showing with the DPLE. So just to understand, are you taking the same initial conditions that are used from the DPLE and then initializing? No. Okay. Can you elaborate a little bit? Because one thing I was curious about was the difference.
Okay, so what we're doing is that DPLE, it's a DPLE large ensemble initialized. So there's 2 large ensembles, and this is what has been done is that CSM was run with GRA55, I believe, forcing ice ocean simulations.
Yeah.
And that hindcast was used to as initial conditions for CSM large ensemble initials decay predictability study. Okay, what we're doing is just we're taking the atmospheric output from DPLE CSM and we're forcing RASM simulations, but our initial conditions are from RASM hindcast, not from the CSM hindcast. So if you look up on this slide, it's actually initial conditions are for December 2015. So that's a month later, but still very similar. This is the CSM initial conditions from that ice ocean force reanalysis simulation.
Mm-hmm.
And this is our RASM hindcast with GRA55 for the same time period initial conditions. And then we're using the atmospheric forcing from CSM DPLE to force RASM along the lateral boundaries. And we also, I didn't explain that in details, we are using nudging about 500 millibars in the atmosphere over the Arctic. And we're driving that way regional model, fully coupled system to do this dynamical downscaling.
And have you looked at the cross-ensemble statistics that you can get, multiple instances of the atmospheric forcing from the DPLE?
So we've run 10 ensemble each. And that kind of comparison, we have looked at comparing the CAS extent and CAS volume. Those results are representative of the ensemble mean of the 10-member ensemble mean. The DPLE large ensemble, they had 40 ensemble means, but only 10 of them, they had the atmospheric output that RASM needs to do the downscaling.
Mm-hmm.
And similarly, so we just to make sure that it's not just one model simulation with downscaling, we did this simulation with E3SM, and we're getting very similar qualitative results in terms of the RASM not carrying the biases from the global model, and it's surface physics dominating the ice conditions.
And I guess in terms of the model spread, do you see a similar model spread for the downscaled results as you do from the DPLE?
So the RASM being more constrained along the outer boundaries probably has, if you would look at RMSE or some other statistics, probably it's not as wide as the DPLE or global model, but generally comparison are very similar in terms of the ensemble members spread. So in my slide for the RASM configuration, if you go to that website, there is some information about the 6-month predictions, and there is a shading provided on that slide on those predictions, which is the ensemble member spread in terms of 6 months prediction forecast.